Hello guys, welcome to the next lecture. Please turn your cameras if you can do that. I really appreciate seeing your faces. And if you have any questions, you can always ask me, especially after class. I'm always happy to stay after class. And we will discuss and solve those questions. Probability, if you approach it with logic, is not so terribly difficult. Combinatorial analysis, lecture 3. Combinations. So this is the main problem. Suppose we have n students altogether, and we want to select out of them r students, right? Now, a selection just means an ordered selection. You can imagine that the students are to be standing on one of the trays. Either they will be standing on the red tray, or they will be standing on the blue tray. And if they stand on the red tray, they have been selected. You understand? That's you agree that, at least logically speaking, that indicates selection. Wonderful. So then if I have the situation, then I have altogether on the students standing on this tray can be arranged in n factorial ways, standing on both trays to be precise. N factorial ways if there are n students. And the students on the red tray can be sorted. So they can just jump over one another. So 2 can be the first that you see from the left, or 1 can be the first from the left, or any other ordering, as long as the same students are on the red tray, they still have been selected, and as long as the same students are on the blue tray, they have been selected. So altogether, if I write n factorial, I have created r factorial times n minus r factorial over countings. I hope you see that. Any questions? Do you see why I created r factorial times n minus r factorial over countings? Because those r objects can be arranged in any r factorial ways, and those objects on the blue tray can be arranged in any n minus r factorial ways. And any rearrangement means the same situation. It still tells you selected and not selected. Good. So altogether, by overcounting, we have n factorial divided by r factorial n minus r factorial. Before I continue, guys, any questions? Don't be shy. If you don't understand this calculation, please ask me a question. Good. Then we have that n choose 0 is equal to 1. That's by default, because if I'm to select 0 students, there is only one way to do that. There is only an empty set that I count. It's the photograph that has no students present. And by that, we have to, for this formula to still work, I will have to make 0 factorial equal to 1. Because you see here, I will have to, for instance, divide by 0 factorial in this situation. So I would like it to be equal to 1, since this would be n factorial over n factorial. Good. And here is a very basic situation of just that general example that was described. So we have 3 students from a group of 4 will be selected to go to Greenwood Cemetery. That's where I hold office hours, if people want to see me in person. So this is the tray containing the 3 students that will come. And in this case, green tray will hold the student that is not going to come. So we can create a Kafka protocol to indicate what just happened by listing the students according to the number assigned to them from smallest to largest. So you see, I will have this box to list the students that were assigned to go as 1, let's say 3, and maybe 4, for instance, and maybe not in this picture here, right? In this picture, it's 1, 2, and 3. But imagine that I write 1, 3, and 4. That means student 1, student 3, and student 4 has been selected, and student 2 has not been selected. I write the box here. Yes. And I cannot write this code this way. So if I look at this situation, then I clearly see that there are 4 documents that I should have. This is basically without overcounting, because I can just pay attention to the student that was left out, either student 1 or student 2 or student 3. So there are 4 documents, or student 4, right? 4 documents. Good. So 4 choose 3 is equal to 4. And if you calculate it as 4 factorial over 3 factorial 1 factorial, that still gives you 4. Here is another example. From a group of 5 women and 7 men, how many different committees consisting of 2 women and 3 men can be formed? This question has a second part, but we'll mention it in a moment, right? We're just up to here. So I want to form a Kafka protocol. So I have the selection. So I have a box for women and I have a box for men. And the women are labeled 1 through 5 and men are labeled 1 through 7. And I will write the code for women in order from smallest to largest, and I will do the same for men. So for instance, I might have written 2, 5, 1, 4, 7. That means that woman number 2 and woman number 5 are part of the committee. Men number 1, men number 4, and men number 7 is part of the committee. So this code counts without overcounting precisely what has just happened. You see, this code where I keep order. But how do I count how many possibilities are there to fill the left box? Well, the left box can be filled in any number of 5 choose 2 possibilities. Do you see that? Any of the 5 choose 2 possibilities, because this is just selecting 2 individuals. And we know that if the procedure we just outlined above, we can imagine 5 factorial, arrange them in any direction. 2 are in the red tray and 3 are in the blue tray. That's why we divide by 5 factorial by 2 factorial, 3 factorial. That's how we calculate this, yes? And whatever happened here, the left box, I pick 3 individuals out of 7. So it's 7 choose 3. That's how we designate it, and how this is counted. Again, guys, you understand it. 7 factorial, 3 divided by 3 factorial, and 4 factorial. Any questions so far? So the answer to this problem is by basic principle of counting. How many ways to write a code here? There are 5 choose 2 codes to put here, and 7 choose 3 codes to put here. And by the basic principle of counting, any code that I write here does not influence the possibilities for the right box. So it's this number multiplied by this number. 5 choose 2 times 7 choose 3. You all with me, guys? And don't be shy. I mean, I know that everyone looks smart, and that's happened to me. I always imagine everybody is smarter than me, but sometimes it's not true. So same thing for you, right? So if you think, oh, you are the only one stuck, most likely everyone did not understand a single word I said. Good. So don't be ashamed of stopping me if something is unclear. Very good, Jacob. Very wonderful. Thank you. So up to here, you follow, guys. I know it always, I'm very paranoid. I hope you follow, you know, with what should you follow? You should follow with this or with this, with your heart, with your stomach, maybe even, right? Aristotle, I think he mentioned that he had a theory that the brain is just nothing but a sponge to cool the blood. I guess he always imagined that intuition happens in the stomach. So that you must do the same. You must feel it. Now, the second part of this question is this. What happens, guys, if 2 of the men are feuding and they will not, or feuding, right? I read it like in German, right? Feuding. They are feuding and they will not be serving together. Yes. So it's the same situation, but they cannot serve together. Well, careful, guys. What happens there? You see, do we have more possibilities? If we multiply, just again, the same problem, but now 2 people, 2 men cannot be placed together. So what do we do then? Any ideas? I know I'm not going to give you a lot of time for them as I have to rush, especially at the beginning. But I'll give you 3 minutes. Try to figure it out in 3.
Should you figure out how many men or how many groups have both men by doing a combination of 7 choose 2 and then throwing that number out from your total?
Well, 7 choose 2. If it's both men, then you probably mean 5 choose 1 because
Right.
you already chose those 2 people and you need to add 1 more to make it 3, to make it a group
Right.
of 3. But yes, that's a very good idea. Thank you. So here is one strategy that we can approach it with, guys. Put in this box for men. Imagine that it happened that men number 1 and men number 2, the 2 enemies, were selected. So I label them as 1 and 2. And then this box has 1 more entry to be a complete collection of men. Yes? So how many available numbers are here? Well, we used 2 of the numbers. We had numbers 1 through 7 for the men. We used 2 of them. So we have only 5 available. And out of them, we must pick 1. So it is 7 minus 2 choose 1 or 5 choose 1. Correct? 5 choose 1 now. Do you understand, guys, what happened? It's 7 minus 2 choose 3 minus 2. So it's 5 choose 1 to fill in this box. But this box can be filled in any which way. So there were, I believe, 5 women. And we need to pick 2 of them. So it's 5 choose 2 possibilities to fill in this box and 5 choose 1 possibilities to fill this box. So it's 5 choose 2 times 5, right? That's how many combinations there are where you have 2 enemies in the same committee. So altogether, we take all the committees minus the committees with enemies because those committees cannot exist. So I toss away documents, I subtract. Because I toss away the documents that represent situations that cannot occur. Do you understand? What I personally imagine is I print every code out on a separate piece of paper, and the code looks like those 2 bars filled in, and I have this many papers. You can just multiply the number and you see how many papers you have. Out of them, I remove manually all documents that have the code 1, 2 for men. And that's how many documents I will remove. Yes? So the remaining number is how many documents I have available for committees that can take place. Good. Not so bad. I'm very glad that we are still following. Another way, guys, to do that is as follows, right? I can consider the situation where both enemies are excluded. Enemy number 1 is in, enemy 2 is out, and the converse, enemy 2 is in, enemy 1 is out. So if both enemies are excluded, it's 7 minus 2 choose 3. Do you agree? I need to choose 3 people. They are none of the people 1 and 2. So I have 7 minus 2 choose 3. 5 choose 3. And then this one is, let's say I have the number 1. So my code for men, the section for men, this section begins with 1, but there is no possibility of picking 2. So that would be 7 minus 2. I'm only allowed to pick from numbers 3, 4, 5, all the way to 7. So I have 5 numbers. Out of them, I pick 2. Yes. And then I have this other situation where I have 7 minus 2 choose 2. It's a symmetric situation where number 1 is out, number 2 is in, and I have to add additional 2 numbers. Yes? So altogether, it's 5 choose 3 plus 2 times 5 choose 2. So what I see is I also see this nice identity that 7 choose 3 minus 5 choose 1 is the same as 5 choose 3 plus 2 times 5 choose 2. So this is where I exclude from the possibilities from the combination of men, I exclude the situation where both enemies are together. And here I just separately count documents where the enemies are not in And then the middle pile is where you have papers, middle pile of papers, where I have enemy 1 in, and the third pile of paper I have enemy 2 in. Yes, so that's why it's 2 times 5 choose 2. So there are actually 3 piles of documents, I imagine. I partition just the men 7 choose 3 possibilities into 3 piles, and because we're counting exactly the same thing, you see this is an identity, and so we have this identity. So this is the first way we calculated it, by removing the enemy committees, and this is the second way of calculating it, by conditioning on whether person 1 is in or person 2 is in or none of them are in. Yeah. Here is yet another example, guys. Let's see if you can do it now, or try to write in the comments if you manage to do it fast enough. 10 women and 16 men. Committee consisting of 7 women and 9 men is to be formed. 5 men are friends and they have to be together. So 5 people always have to be together, all of them. 2 women refuse to serve together. How many committees are possible? Do you see 2 conditions now, guys? There are 5 people, 5 men must either all be in or all out, and 2 women cannot be together. How many possibilities? Type in the comments if you can. The way you can write combinations, because it's difficult to do the parentheses, you can do, let's say, 7 choose 3. 7 choose, 1 second. 7 choose 3 can be written as 7C3, for instance, if you can write it this way, like in the calculator. Good. All right, guys, let's work on it together. So first of all, I want to create a document. I mean, at least I advise you to do that because it helps you be sure that you are not making an error. So in this document, I see women and men. So we can label women 1 through 10. 1 and 2 are the enemies. Label men as 1 through 16. 1 through 5 are friends. How many ways are there to fill in women? Well, 10 choose 7 is all possibilities for women. Out of 10, we need 7. And we don't have the possibility woman 1 and woman 2 together. So that's 10 minus 2, choose 7 minus 2. In other words, 8, choose 5. You agree? 8 choose 5 situations, 8 choose 5 of the codes here will correspond to impossible situations, right? I cannot have the code being 1, 2, right? The code here, you remember, guys, what is written here. So how many digits is this code, or how many numbers is this code? Not necessarily digits. How many numbers are in this code? Type in the comments, just a quick sanity check. 7 numbers precisely. And those numbers, guys, must be in order. You always write them from smallest to largest, you see? That's the condition I decided to use here. Because if you choose people, you can always sort them, right? If they're not, when you choose, it's an unsorted choice, but you can always sort them. And so you list the sorting by smallest to largest number. So this code cannot begin with 1, 2. It can be 1, but then 2 is omitted. It can be 2, but then 1 is omitted. So that's the situation for women. For the men, I can do it the following way. I can see the code. If I have the number 1, then I have 2, 3, 4, 5. If I don't have the number 1, then I don't have every number all the way to 5. Right? So friends are in. I have friends are out. So 16 minus 5, choose 9. In other words, I have to choose 9 men. But 1 through 5 are not available. So I see 9 numbers here, but not 1 through 5. So there are 16 minus 5, choose 9 possibilities of doing that. Or I actually see the numbers 1 through 5. And if I see numbers 1 through 5, I must see additional numbers that complete it and make it a code of length 9. So it's 16 minus 5, choose 9 minus 5. Are you with me? You see why 16 minus 5? 16 minus 5, because for the second scenario where the friends are in, I imagine numbers 1 through 5 are filled in, and so I don't have access to them. I have 16 minus 5 remaining numbers. I need to complete the sequence of numbers to be of length 9, and 5 already are there. Good. So that's it. So then it's just 9 minus 5. And so the answer is simply now women times men, just because it's now basic principle of counting. The numbers that the number of outcomes into this box times the number of outcomes into this box. So it's 10 choose 7 minus n choose 5 minus 8 choose 5 times 11 choose 4 plus 11 choose 9, I believe. Good. Let's end this, guys, with a pretty difficult question. Maybe the solution is here, but maybe I should just state the question and let you think about it for next time. Maybe we can repeat the question on Wednesday. You'll decide, okay? So this is a difficult question if you haven't solved one like this before. We have n antennas, or maybe think of them as batteries. They are either defective or functioning. So m are defective and n minus m are functional, right? So I mean, maybe batteries look the same, or I'm not sure about antennas, but let's say batteries look the same. Either the battery is depleted or it's not depleted. Now, you cannot distinguish between defectives, and you cannot distinguish between the functional, but you can distinguish functional and defective. So how many linear orderings are there in which no 2 defectives are consecutive? In other words, the device that you have here will work as long as no 2 defectives are next to each other. They must be separated by at least one functioning antenna. You understand? So this question is slightly difficult, or maybe very difficult, because to solve it, you probably have to pay attention to something else. Not to the antennas, but maybe to something around it that will give you information about the antennas. Make sense? Probably doesn't. Do you want to think about the question and hopefully not pick at the solution? Or do you want to listen to the solution right away? Please let me know quickly. So Ryder wants the solution right away. Nicholas wants to think. Come on, guys, vote. Solution, I imagine it's just right away give you the answer, yes? Well, I mean, it looks to me like it's at least 50-50. So here is what we will do. We will return to this question on Wednesday, guys. Write it down and hopefully write it down on a separate piece of paper so you don't have the urge to look into my notes, which I'm sure you do sometimes, right? Unless you don't know how to find them. Do you all know how to find my notes? Yes? Good. That's nice. And if you want to watch the videos again, you know where to find them, correct? Guys, my notes are on etkin.com. You see etkin.com, this website. And you can just look into stat 311 and you will find the notes. Good. Let's move on. We will return to that question again. We are going to talk about the binomial theorem. So let's see if you have wondered what it means to multiply. Guys, if I am going to multiply A1 plus A2 times B1 plus B2 plus B3, what in essence is happening? What in essence is happening here? So look at the situation, guys. When you expand the parentheses, you essentially have A1 combined with B1 and A1 combined with B2 and with B3. And A2 is combined with each of those separately. So there is exactly one match between each A and each B. They meet exactly once. Yes, so it can be written in a sigma form, that means sum everything, where the first box in red is either A1 or A2, and the second box is either B1, B2, or B3. My immediate question, how many terms are in the summation, guys? I mean, it's too obvious in here, but do you see why? What do you do to... Yes, I'm just expanding the terms, and I just want to know how many, once I expand, how many summons, how many entities between which I see plus are there. So this is either, you see, notice this pattern, guys. When I expand parentheses, I will always have a match between some A against some B. So A is matched against B, and each A is matched against each B exactly once. You see that there is A1 only means B1 once, only means B2 once, only means B3 once. It's very poetic. You only meet one person once and then lose them forever. Yes, guys, the answer is, Nicholas, correct. It's 6, or as Ryder noted, even better, 2 times 3. Right, guys? 2 times 3 because we have those boxes, they belie or they hide that basic principle of counting, that for any entity that you put in the left box, you have a choice of 3 entities in the right box. Yes, so one of the B's goes here, one A goes here. Now, it's not any different if I have a combination of 3 parentheses, where in the first parentheses, I consider those A1, A2. Then here I just wrote it B1, B2, B3, and onwards, right? Let's see. So it's pretty annoying to expand this, but rest assured, if you think a little bit about how parentheses are expanded, the summation, once you expand it, the result is going to be a summation of terms, and in the terms, I will have each A against one B against one C. You understand? So each of the A's is meeting each of the B's is meeting each of the C's, and that happens exactly once. Yes? You should, by the way, be very thankful that I think Zoom has modified its interface and it made it very buggy, because I would have been torturing you with the poetry, right? Without stuff, songs and whatnot. And now I'm not sure I can. 24, well, yes, let's see what happens here, guys. It's 2 possibilities for A, 3 possibilities for B, and 4 possibilities for C. 2 times 3 times 4, very good. Do you understand that, guys? So that's how many summations are going to happen. That's very important for the next process that we will try to understand. how do we expand x plus y to the power of n? That's the binomial theorem. It's a very important theorem. So if I write it to the power of 1, then it's just x plus y. If it's to the power of 2, I mean, I put the markers under the x, but it should rather be under the parentheses, right? It's, I would say, first parenthesis, second parenthesis. Okay, so it's going to be one term from the first parenthesis matched against one term of the second parenthesis before I simplify anything. You agree? Without simplifying, it's going to be this term times this term. So that means first term from first parenthesis against first term from second parenthesis. First term from first against second from second. And second from first against first from second. Second from first against second from second. I hope I haven't confused you. Good. So they're all together. How many terms, how many additions do we have before we simplify? How many additions do we have, guys? Please type in the comments if you follow. Absolutely. We have 2 times 2 or 4 additions. You see, because by the basic principle of counting, it's adding over a meeting where of the first guy against the second guy. Good. Now we are going to simplify because you see, guys, if it's x against y or y against x, it's really the same thing that we're adding because of multiplication's properties. Yes, so I can group it into fewer terms based on the number of times I see x, right? Do I see x 0 times? Do I see x once? Or do I see x twice? Do you understand? In other words, if I see x 0 times, it means second was matched against second, right? So it's only one possibility, right? Y squared, only one possibility. We chose this and this. Now, if I see the term xy, that means x appeared once. That means what must have happened? Either first parenthesis contributed the x or second parenthesis contributed the x. That's why we have 2 possibilities. Do you see that? It's either x1, y2 or y1, x2. Are you with me? That's why the number here is 2. And of course, if it's x squared, that means that first parenthesis contributed the first term and second parenthesis contributed its first term. Good. Now we are going to try to do the same process with general power n. Are you ready? So n could be 1,000,000. Let's see if we can do that. If n is very large, we just have more boxes because we have a box for each parenthesis. So we have a box for first parenthesis, we have a box for second parenthesis, all the way to a box for the nth parenthesis. And what happens is the term from each parenthesis, right? It's either x or y. Do you agree? Here it's either x or y. Here it's either x or y. If I don't simplify, just a quick question, guys. If I don't simplify, how many terms am I going to add? Write it in terms of n. If I don't simplify, how many terms am I adding? Very good, Gustavo. Right? This box has 2 possibilities. The next box has 2 possibilities, right? Because each box contributes either the left guy or the right guy, either x or y. Yes? So 2 possibilities times 2 possibilities times 2 possibilities, 2 to the power of n, which is a huge number. Yes? Looks like a huge number. Now, if I simplify, guys, don't tell me the terms, but if I do simplify, how many summons do I get? How many terms that are blocks that I will add if I simplify? Can you tell me? With a very simple number. It's now a very simple number. How many do I have if I do simplify? Okay, some people say n. Let's see, is it truly n? Guys, what's the possibility? Either I see no x's, or I see 1x, or I see 2x, or I see 3x, or all the way to seeing n copies of x, the x to the power of n, right? So do you see what I'm saying, guys? Either 0 x's, that's one block. I combine all the cases where I have 0 x's. I will combine all cases where I have just 1x, all the cases where I have 2 x's, 3 x's, all the way to n x's. So the answer is n plus 1. Very good. You noticed it now, right? It's n plus 1 terms if I simplify 2 to the power of n compared to n plus 1. Huge difference. Do you agree? Insane difference if n is a big number. That 2 to the power of 56 is insane. But 57 against 2 to the power of 56 is a trifle. Good. So it's n plus 1. And here is that simplification carried out. You see? Y to the n minus 1 all the way to x to the n where it's y to the power of 0. Yes. And then I have to just count how many situations do I have in which I have y to the n. So for the first coefficient, how many ways are there to get y to the power of n? Well, that's very easy. If it's y to the n, then each parenthesis contributed a y. Do you agree? There is only one possibility, because each parenthesis had to contribute a y to achieve this y to the n. Do you agree? Now, without too much thinking, let's just check, guys, if you can do that. What should be the coefficient here? So this coefficient is 1. Do you agree? This coefficient, if I write it down, it's, well, let me write it in red. This coefficient is 1. Tell me, what is this coefficient? Okay, one person sees this. Okay, now the answer is indeed, as you're beginning to see, the answer is n. You can write it in so many other ways, but the answer is n for a simple reason, that which parenthesis contributed the x, it's either first, second, third, all the way to n, and the remaining parentheses had to contribute a y. Do you see? The answer is the second coefficient must be n. You see where the n comes from, guys, because there are how many possibilities? Either first parenthesis contributed the x and the rest are contributing y's, or the second parenthesis contributed that x. The x came from what parenthesis? Where does he belong? Very good. Now, what is the general situation is what we are trying to understand. What's the coefficient here next to x to the power of k, y to the power of n minus k? Do you see what happened here, guys? X to the k, y to the n minus k. What's the coefficient? Can you tell me? And maybe a y. It's not easy to type a y, but maybe you can have a very short sentence to say why that's the case. I will speak it at least. Well, as some of you have noticed, the answer is n choose k. Why is it n choose k, guys? What are we selecting, guys? You see, n choose k means that we are selecting something. We had this analogy. We have students that go with me to Greenwood Cemetery. Yes? The students in this situation are what? Who are the students? So who are the students and what does it mean here to go with me? What are we choosing? No, not the X are the students. Sometimes you want to mark the students with an X, but those are not the students. All right, let me tell you what I think. So the parentheses, guys, x to the power of k means that which of those n parentheses were chosen, and chosen to do what? To contribute an x. You understand? The n is the number of parentheses, in the sense that we have here parentheses 1, parentheses 2, all the way to parentheses n, right? Now, how do I get x to the power of k? I can only get it if I make k of the parentheses, so I have n altogether, but k of them have to create an x or contribute an x. Do you agree? So which of those parentheses will contribute the x? Is it parentheses 1 through k, or is it parentheses 2 through k plus 1, or some other collection of them? Which of them contributes the x? The remaining parentheses have to contribute a y. Do you agree? So I don't need to even worry about the remaining ones. So those that are chosen will contribute an x. Those that are not chosen will contribute a y. And there are n choose k ways of picking those parentheses. So they are the students in this example, right? And going to Greenwood means deliver x, right? Isn't it nice, guys? You see my my Galgenhumor, my great humor, contribute an x, right? To Greenwood. Well, you don't find it funny, but I do. So those parentheses that contribute the x, they are the ones that are chosen. There are k of them. That's n choose k. The remaining will contribute y. How I got k? K is just an arbitrary index. I'm just understanding how to create coefficients over here. What I'm saying is that this coefficient is n choose 0. Do you see why it's n choose 0? Because no parentheses, none of the n parentheses was made to contribute an x. And n choose 0 ends up being 1. This number here is, there is one x, right? X to the power of 1. That means that one solitary parenthesis contributed the x. So this means n choose 1. Yes? Now the next term would be, if I write it here, it's x squared y to the n minus 2. Now two parentheses were chosen to contribute an x, so it's n choose 2. You with me? And in general, if it's k, k is just instead of writing n choose 0, n choose 1, n choose 2, I just say, oh, if you want to know what's the coefficient next to x to the power of 5, that would be n choose 5. And the coefficient next to x to the power of 7 will be n choose 7. Yes? So the coefficient in general is of the form n choose k. And the last one is, of course, n choose 1, n choose n, I'm sorry, because all of them were contributing an x. Good. Here you can see that situation in expanded form. N choose 0, n choose 1, all the way to n choose n. Good. So comprehension check, guys, just to be sure. Here is x squared y squared in the expansion of x plus y to the 4. What's the coefficient of x squared y squared, please? Can you tell me what's the number? So if I expand x plus y to the 4, what's going to be the number next to x to the second, y to the second? Right? So it means that out of 4 parentheses, we choose 2 to make the x, and the remaining 2 will make the y. So it's 4 choose 2. Yes? You follow how that works, guys? So I make the parentheses the students, so I give them numbers, first, second, third, and then I put them on the tray. I imagine kind of switching them, putting them on a tray, on the red tray. I will put 2 of them, and on the blue tray, the other 2 of them. So that will be 4 factorial divided by 2 factorial, 2 factorial. That's 4 choose 2. Yes? Good. And here I try to explain by showing you what could have happened. You see, guys? It could have been this situation. It could have been this situation where the numbers indicate parentheses, where it came from, right? So it could be that first and second parentheses made the x. It could be that first and third parentheses made the x. There are altogether 6 possibilities. And I decided to list them out for you, just in case it helps. You understand? So this is just showing you how x squared y squared could have been created in this pretty long product. Good? Okay, guys, here is a comprehension check, a little bit harder one. Can you tell me what is 8 choose 0 plus 8 choose 1 plus 8 choose 2 all the way to 8 choose 8? Can you tell me what happens here? What's the answer? What does it equal to? Good. We can solve it in maybe 2 ways. You can figure it at least several ways. Very good. 2 people see that. Well, guys, each student is like a parenthesis, yes? So if I have 8 students, I have 8 parentheses. And each parenthesis, that's one way to solve it, each parenthesis can contribute, so parenthesis 1, parenthesis 2, parenthesis 3 onwards, can contribute either be present or be absent, yes? Either 1 or 0, yes? So what is 8 choose 0? That means that no student came to my class. 8 choose 1 means 1 student came to my class, right? 8 choose 2 means 2 students came to my class, and so on, right? 8 choose 8 means I have perfect attendance. So another way to list attendance. So I see that I'm counting the possible attendance I have before I began my lecture, if I have 8 students, yes? So instead, I could just have this bar with student 1, student 2, student 3, 4, and onwards, right? And I write absent or present. I put either 0 or 1, or 0 or 1, or 0 or 1. So I have 8 boxes. Each of them is either 0 or 1 without affecting the next box. So I have 2 times 2 times 2 times 2, 2 to the power of 8 possibilities. 2 to the power of 8 possibilities to accomplish it. You agree? That's one way to see this, to see the answer. I just see what we're counting attendance records, and I can just do it all together. Here I group situations where I have no students, situations where I have 1 student, 2 students. I kind of break the 2 to the 8 documents into different attendance types based on number of people that come. Another way to observe that is, so I gave you the second way to observe it right away, you see. So what's happening is 1 through 8, 0 through 1 is the numbers I put here. So it's 2 to the 8 possibilities. Or you can observe that I can multiply this by 1 to the power of 0, 1 to the power of 8 without changing anything. This I can multiply by 1 to the power of 1, 1 to the power of 7. And in general, the kth term I can write as 8 choose k, 1 to the k, 1 to the 8 minus k. And I recognize this is a binomial expansion. So that's the expansion I get if I just write 1 plus 1, and I just think of 1 as x and as the second one as the y. So it's 1 plus 1 to the power of 8, which is 2 to the power of 8. So I could have used binomial theorem if I decided that it's better. Yes? Here is a useful identity, guys. So very useful, I think. So we're going to learn. That's pretty much, it's very exciting what happens sometimes in mathematics. It's like you might have something uninteresting, but you realize it's a code, right? So somebody sends a message that says, "Mother, I'm doing very well." And it's really, it means that there are two Navy ship parked right now at the dock, for instance, right? So then of course, the message is much more interesting. So that's what you do in combinatorics. You are trying to decipher what is the message, what are we talking about. So you see n choose r is equal to n minus 1, r minus 1 plus n minus 1 choose r, right? So we see this situation, what somebody might be talking about. So here is a way to do that. So we have a class in which we have n individuals, and one of them is Jimmy, and Jimmy is rather special. It's a golden boy. So I label Jimmy as n, and the remaining kids as 1 through n minus 1. Yes. So here I choose R students, and I want to know whether Jimmy is part of my selection or not part of my selection. Yes. So if I choose R students, how many situations are there in which Jimmy is present? So if Jimmy is present, that means that that number is so pile 1 is where Jimmy is present. So I don't know what the first R minus 1 numbers are, but I know the last number is n. And in the remaining pile, I know there is no n, but there are still only n minus 1 numbers available for me. Are you with me, guys? So whether Jimmy is in or not, in my document of selection, I have n numbers that I have to place in. Yes. So in case Jimmy is not available, in other words, the combinations where Jimmy is not in, that's this combination, then I have n minus 1 numbers, 1 through n minus 1. And out of them, I must make a selection of R individuals. On the other hand, if Jimmy is available and I place him in my group, then I have to complete by choosing additional R minus 1 individuals out of n minus 1 remaining individuals. So that corresponds, this first box, this thing corresponds to the situation. Yes? And there are n minus 1 choose R minus 1 possibilities. Good? So now I see that the identity must be true, because if I select R individuals, it must be the case that either Jimmy is part of the selection or not part of the selection. Did you understand the explanation, guys? This is called a proof by story or combinatorial proof. So remember that, guys, when I ask for combinatorial proof, I don't want you to calculate, because calculations are pretty tedious and boring, even if you are able to do that. And it means that you still don't understand what's going on. But we kind of prove this, that this is an identity, because we know that either Jimmy is part of the selection or Jimmy is not part of the selection. And this counts the possibilities where Jimmy is part of the selection, and this counts the possibilities where Jimmy is not part of the selection. Yes? Now we can talk about Pascal's triangle. So guys, any questions before I move to Pascal's triangle about this? Or are we clear? Right, yes, if it's clear or something like that. So I know I haven't lost you yet. Okay, one person said no. Let's see. Yes, I will just try to quickly repeat. I want to understand this combinatorial identity. I want to know why this is true, or even hopefully see that such things can be true. Yes, without having, in other words, just coming up with this expansion without anybody teaching me. Now, why is this a combinatorial argument? You just realize that somebody is carrying a calculation in two different ways. So there are two different ways that count the same thing. So all you have to figure out what is being counted. So here, let's say we have a class of n individuals, and R of them will go with me to a trip, to a school trip. Yes? Now, I want to know very specifically if Jimmy is part of this trip or not. So that means that I break my possible documents. I will pick a document, and on the document, I see the codes for the students that are coming. Yes. So I will either pick a code where the number n is part of the code, or I pick a document where the number n is not part of the code. That means either Jimmy is in or Jimmy is out. And then how many documents are in the pile where n is part of the code? If n is part of the code, then the remaining segment is completed out of n minus 1, right? So basically I have numbers 1 through n minus 1 remaining individuals that I have to list to make it a full code. The code lists R individuals. One individual is n, and I have R minus 1 additional numbers I have to pick from n minus 1 available ones. Do you understand why n minus 1 is available? Because Jimmy is already in, so there are only n minus 1 additional students. Out of them, I have to pick R minus 1 students. Yes, so that's counting the situation where Jimmy is in, the possibilities where Jimmy is part of the trip. And here on the right is the situation where Jimmy is not part of the trip. Yes, you can see that Jimmy is not part of the trip because you see the denominator, so the bottom part is R. It means I need to pick out of n-1, I need to pick the full team of students that will come. But n-1 indicates that Jimmy is not part of my possible choices. Clear? So I basically broke this pile into two piles. They're not of equal size, but what the documents in this pile plus the documents in that pile and end up being all documents. So I see that this is true. Okay, guys, so you can think about it and ask me the same thing a million times, especially after class. Yes, if it is not clear. Now let's talk about Pascal's triangle. So you see, you might know this tool as a very useful way of expanding x plus y to the power of n, to expand the binomial formula and actually find the number. So for instance, what you do is you write 1, and then you write 1 and 1, and then the next expansion is going to be 1 unit more. So first is 1, then this width is 2, this width is 3, this width is 4, 5, and onwards, right? So the pyramid is growing by 1 digit wider, by 1 number wider. Now these numbers are 1 and 1, and then this is 1, and then the middle number you just place between 1 and 1, you place the sum. 1 plus 1 is 2, and then you write 1. So 1 to 1, that means x to the power of squared times 1 plus 2xy plus y squared. Yes, plus 1 times y squared. And if you want to know how to expand quickly x plus y cubed, what do? You write an extra 1 here, and then between 1 and 2, you write their sum, it's 3. Then between 2 and 1, you write again, because their sum is 3, you write a 3. And you complete it with a 1. So you have 1, 3, 3. That means that x plus y cubed is x cubed plus 3x squared y plus 3xy. Yeah, so 3y squared, yes, 3xy squared plus y cubed. And you do the same thing for, you expand x plus 4 this way. So those are the coefficients for the expansion of x plus y to the power of 4. Yes. Now, this Pascal's triangle is actually working on the Jimmy principle, right? And choose k or n choose r is equal to n-1 choose r-1 plus n-1 choose r. It's working on this Jimmy principle, on that one. Now, why is that the situation? Let's try to understand it. Yes, Grant, you wrote it exactly correct. Let's you see, so here is that situation, right? You see the expansion for x to the power of 4. Here are the coefficients for x to the power of 4 that I wrote here. Yes, without the, let's say, without saying 4 choose 2 or 4 choose 3, I actually can calculate the actual numbers pretty easily. Yes. Now, why it worked, guys, think about what is this coefficient, right? So the coefficient 3 here. What is that coefficient? This is supposed to be 3 choose 1, right? But by Jimmy identity, 3 choose 1 is the same as 2 choose 0 plus 2 choose 1. 2 choose 0 is 1, 2 choose 1 is 2. Do you see? So this 3 was obtained as a sum of 1 plus 2. You understand? Or so it's a recursion. For example, what is this 6, guys? This 6 that you see over here, it's supposed to be the coefficient next to x squared y squared. Yes. Now, if it's x squared y squared, and the expansion is it's to the power 4, so it's 4 choose 2. What's 4 choose 2? 4 choose 2 is, you see, this is 2, right? 0, 1, 2, right? 4 choose 2. Now 4 choose 2 is the same as 3 choose 1 plus 3 choose 2. 3 choose 1 is 3 and 3 choose 2 is also 3, you see? So the Pascal, this coefficient, that's why the coefficient is the sum of those two above it. Do you follow? So you can just quickly fill in the pyramid and just obtain the coefficients just because of that. Any questions? We now understand why Pascal's triangle is the way it is, yes? Of course, Gustavo. Okay, look at this two. What is this two, guys? Right. So this, look at it. It's x plus y squared. This third row corresponds to x plus y squared. Okay. Now x plus y squared means we have 2 choose 0, 2 choose 1, and 2 choose 2. Yes, that's what we need to obtain. 2 choose 0, 2 choose 1, 2 choose 2. 2 choose 0 means that it's x to the power of 0. 2 choose 1 means we have 1x, 1y. 2 choose 2, we have 2 x's, for instance. Yes? So how do I obtain, let's say, 2 choose 0? It's very easy, right? 2 choose 0 is just 1. What about 2 choose 1? I mean, it's also very easy. 2 choose 1 is 2, right? But let's say I want to calculate it in terms of even simpler coefficients. So 2 choose 1, it's the same as 1 choose 0 plus 1 choose 1. A bigger number, better, let's say this 3. This 3 is 3 choose 1. 3 choose 1 is the same as 2 choose 0 plus 2 choose 1. So 2 choose 0 is 1, and 2 choose 1 is 2. So we have 1 plus 2 is equal to 3. It's the Jimmy identity. You see what happens? The R indicates the position in the, so n choose R. N indicates the layer of the triangle. So if n is equal to 3, then I'm in this layer, right? I'm in this layer. And the R indicates if I'm in this row, where do I go, right? How deep into the row I go. So if R is equal to 3, I go all the way to here. If R is equal to 2, I go to here. If R is equal to 1, I go to here. If R is equal to 0, I go to here. Yes? So let's say 4 choose 3 means this is 4. This is 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3. I look here. Okay. And then how do I obtain this coefficient if it's 4 choose 3? It's the same according to this formula as looking at the prior row at the higher level of the pyramid and looking at the position right below, right? If this was position 3, I look at position 2, and I look at position 3. So R minus 1 R. So I look in the prior row, position 2 and position 3. Clear? Okay, guys, and if it's not clear, you just talk to me more after class. I'm happy to re-explain it in slowly. Here is a comprehension check, guys. I want to see if you can simplify this formula by telling a story. It's called combinatorial argument. So that means don't calculate anything, but realize that somebody is doing a counting and figure out a simpler way to count or a different way to count, right? So we have n choose R, m choose 0, plus n choose R minus 1, m choose 1, and onwards, right? You see what happens here, right? So we choose less of n and we begin to choose more of m. Yes? And we have summation in between. So what is this equal to? Maybe it has a very simple formula. Okay, good. Ryder, very nice. All right, guys, are we ready? It is, and I know it's a very short duration, but you know you have lots of questions to practice, right? You know where to find those questions, by the way. You can look into my homework section and into exam reviews, where you can find lots of practice. Also, you can find the textbook on my website, or one of the textbooks. Very good, Nicholas. All right, guys, so here is the idea. So we have two categories. We have category N and category M. Yes, maybe that means we have N boys and M girls. Or it means we have two different types of toys. It doesn't matter, right? But we distinguish between two types of objects. And then what happens? We have either chosen R objects all from the category N and 0 from category M. Yes? Or we have chosen exactly one from category M and the rest from category N. Or, you know, all the way to having not chosen anything from N and chosen everything from M. You agree? So what could it possibly be? It means that whatever we're doing, we are choosing R objects. Out of how many? N plus M distinguishable objects, pick R objects. That's the answer. Are you with me? This entire sum is the same as N plus M choose R. Because really, we're just picking this, we're just picking R students, let's say, out of students of type N and students of type M. It's written here as well. Good. This is what we do next time. We speak about dragons and princesses, but I think in 4 minutes I will not be able to say anything interesting. And so I will take your questions if you have any, guys. Let's try. Here is this thing, guys. I wonder if it will work or not. Recordings are posted on my channel. The channel is on YouTube. It's called Arkady Etkin. Very easy to find. Right? There are very few people called Arkady Etkin. Any other questions, guys? All right, guys. There is this thing. I'm not sure if you want to do it or not. That involves translation. There is a very interesting, unique Russian game show, very popular in Russia, but not popular here. And in that game, you have people that are very good at solving riddles. And the riddles are prepared for them already ahead of time. The viewers play against them for money in trying to find riddles to give them and for them not to solve those riddles. Yes? If you are interested, I can show you, if it of course will work with this internet, I can show you, or work with through Zoom, I can show you a question like this. I will have to translate, but let me know if you want it, or do you want to just go home and rest? I will stop the recording.